Hello, welcome to COP 4708. In this session, we will address redesigning databases. To do that, we need to examine the original database, the design of that database, and we can do that through queries that will explore the internal caves of the database. With the need to add more data and with the new software packages and upgrades, it's necessary to look at the option of redesigning your database. And that is important to fix mistakes made during the initial database design and to adapt the database to changes in system requirements. When an organization installs a new information system, that will cause changes in system requirements, which will make users ask for system capabilities that can accommodate their needs. One of the ways to query an existing database is a correlated subquery, which looks similar to subquery that we processed or we did in chapter 7, but processing it will be different. In the correlated subquery, the processing is nested. That is, that's a row from an upper query statement is used in comparison with rows in a lower level query. While in the regular subquery, the processing from the bottom up. The regular subquery was introduced in chapter 2, where it contains two separate tables in the levels of the query. The example that we used was from the Viewrage gallery database, where we had artists in the top level query, while work in the subquery as shown in the code. But what if I decide to use title to be the alternate key for me? What if there was similar titles? For example, Mystic Fabric. To solve such a problem, we use the correlated subquery, where it contains the same tables in both levels of the query. The subquery purpose is to check if we have in the table title two work IDs with the same title. Once I know that, then I can either change the title or not use the title as alternative key. Also, correlated subqueries can be used to check for any rows that violate the functional dependency. For example, if we would like to check that no two departments have the same budget code, then we use the nested correlated subquery shown here. And as you can see in the code, we have a comparison between the two departments and comparison between their codes. If the two departments are equal, the code should be equal. If they are not equal, then their code should not be equal. Other specialized forms of correlated subqueries are exist and not exist. An exist condition is true if any row in the subquery meets the specified conditions. A not exist condition is true only if the rows in the subquery don't meet the specified condition. We can also use not exist to find rows that have some specified condition to every row of a table. If we go back to the example of functional dependencies, we can use exist subquery to check that no two departments have the same budget code, as shown in the SQL code here. As an example of double not exist, let's assume that we want to know the name of any artist that every customer is interested in. To do that, we can find all customers who are interested in a certain artist, then take the complement. If the complement is empty, then all customers are interested. The first not exist was to select the customer ID from the customer table, and the second not exist is to match that with the artist using the customer artist interest table. You looked at the database and you found that it needs redesign. Let's assume that you would like to change the primary key. Can you do that? What will happen when you do so? What might be affected? What if something failed during the change? When redesigning database, there are three things that we have to consider. First of all, we have to understand the current structure and content of the database before making any structure changes. Second, we have to test the new changes on a test database before making real changes. Third, we have to create a complete backup of the operational database before making any structure changes. And for these two, for the testing and the backup, we actually emphasize on these. Always do the test on a test database. Do not do it on the operational database. Always back up your operational database. Make sure to back up your operational database before you do any structural changes. This is very important, and every database administrator should understand that. The backup is very important. You always have to back up your database to make sure that it's operational at a certain point. One of the techniques that we use to understand the database is reverse engineering. If you remember, in Chapter 5, we developed a data model, then translated that into database design. In this situation, we will reverse the process. That means we already have an existing design, and we will convert that into a data model. But why do we need to do that? Actually, this process will provide basis to design the database redesign, or to begin the database redesign. The best about this model that it's not conceptual, but it's not also an internal schema. It has the characteristics of both. Once we create a model, we study it very well and understand the nature of the database. During that, we should be careful, since in most cases it has missing information. Most of the database that we see outside have missing information. This is a reverse engineered data model that was created by Erwin. If you look at the model, you notice that he came very close in capturing the actual model. The only problem that it did not determine that at least one transaction is required for work. This is a physical model that was developed by Erwin, which is accurate, except the transaction is not required child of work, as stated in the relationship between the two tables. Another tool that we can use when redesigning or trying to understand a database is Dependency Graph. Dependency graphs are diagrams used to portray the dependency of one element on another. Dependency graphs are not graphical displays like bar charts. They are diagrams that consist of nodes and arches or lines that connect these nodes. This is a reverse engineering dependency graph that shows the table customer with two views. The dependency graph will give an idea if change happens, what other parts of the database will be affected, like tables, triggers, stored procedures, relationships. So you can identify the effect that's happening over these components. This dependency graph shows another example of reverse engineering results. It's considered a good starting point, although it's not quite correct. You can see that Erwin was not able to interpret the join that creates the artist work net view. This is a partial dependency graph that was drawn using the results of ER model. Some of the views, stored procedures, and constraints are not shown just for simplicity. Although it's partial, it shows the complexity of dependencies among database constructs. Can you imagine what might happen if you do a change in the transaction table? Look at the relationship that relates the transaction table with other tables, and you can imagine the size of effect that might happen. Before making any changes to an operational database, a complete backup of the operational database should be made. Any proposed changes should be thoroughly tested. You should have actually 3 different copies of the database schema used in the redesign process. One small test database for the initial testing, another one that's large for secondary testing or final testing, and the operational database in case of the not success or not succeeding in the redesign process. Some of database redesign changes are changing tables and columns, such as changing table names, adding and dropping table columns, changing data type or constraints, adding and dropping constraints. There are other changes that's related to relations, such as changing cardinalities in the relationship, adding and deleting relationship, adding and removing relationship for denormalization. There is no specified SQL 92 command to change table name. Unfortunately, the table needs to be recreated under the new name. Then it needs to be tested, and the old table should be dropped. The data can be copied from the old one to the new one, but changing a table name has a number of potential consequences, especially with relationships and referential integrity constraints. Therefore, using views defined as table aliases is more appropriate. Only views that define the aliases would need to be changed when the source table name is changed. We learned in Chapter 7 how to add drop a column using the alter statement. Other column constraints, for example, default or unique, may be included with the column definition. Although you added the constraint of not null for the column, that will be applied to new rows, existing rows, or the rows that will have null values. All the new rows, actually the constraint that you added for the column will be added or will be applied to the new rows, while existing rows will still have null values. There are 3 steps to add not null column. First of all, you have to add the column as a null column. Then you have to add data to every row in that column. After that, you alter that column constraint to not null. To drop non-key column, we use the alter statement with the drop function. To drop a foreign key column, the foreign key constraint must first be dropped. To drop the primary key, all foreign keys using the primary key must first be dropped, then followed by dropping the primary key constraint. To change data type or constraint, we use the alter table, alter column. For some changes, data will be lost, or the database management system actually may refuse the change. To change a constraint from null to not null, all rows must have value first. Otherwise, again, the database management system will refuse or reject the change. Converting more specific data type, for example, date to money and numeric to character or variable character, will usually succeed. Changing a data type from character or variable character to more specific type can be a problem. For example, alter table artist, alter column birthday to numeric. For adding and dropping constraint, we learn how to do that in chapter 7, where we use the alter statement to drop or add that constraint. For example, alter table artist, add constraint, numeric birth year check. The check will be if birth date is greater than 1900 and less than 2100, which is a constraint to check on the value of the birth date to be between 2 numbers. For changing minimum cardinalities, if it was on the parent side, to change from 0 to 1, change the foreign key constraint from null to not null, which can only be done if all the rows in the table have values. To change from 1 to 0, change the foreign key constraint from not null to null. On the child side, actually, all what you need to do is to add or to change from 0 to 1, or drop to change from 1 to 0, which triggers that enforce the constraint. For changing maximum cardinalities from 1 to 1 to 1 to many, if the foreign key is in the correct table, remove the unique constraint that is on the foreign key column. If the foreign key in the wrong table, then move the foreign key to the correct table and do not place a unique constraint on that table. For example, if employee will be the parent table, employees are to have multiple parking permits, we drop the constraint that parking permits employee number be unique. To change the relation from one to many to many, then you have to build a new instruction, a new intersection table, and move the key and foreign key values to the intersection table. This is an example of changing the relation from one to many to many to many, where a new intersection table, customer, artist, interest, was created, and the primary key from each table was copied as a foreign key to the intersection table. When reducing cardinalities, you have to be careful, since it may result in data loss. To reduce many to many to one to many, create a foreign key in the parent table and move one value from the intersection table into that foreign key. To reduce from one to many to many to many, remove any duplicates in the foreign key and then set a uniqueness constraint on that key. To add new tables and relationships, add the table and relationships using create table statement with foreign key constraints. If an existing table has a child relationship to the new table, add a foreign key constraint using the existing table. To delete relationships and tables, drop the foreign key constraints and then drop the table. Once we understand the database from using the reverse engineering techniques, and once we have a data model that I can move forward and apply all the suggested changes for the existing database, then we start the implementation forward, which called forward engineering. Now remember to do changes on a small test database for initial testing, then the large test database for secondary testing, before applying it to the operational database. So we understand the database through the reverse engineering, then we list the changes or suggest the changes needed, then we start the implementation going forward or moving forward. Some software tools can be used to create the SQL code that can be used for implementing the changes, but you have to review that code carefully before using it. So don't depend on these software packages. Actually, review it and make sure that it's creating the code correctly, and test it, then implement on the operational database. And again, be sure to do the testing on initial set, then large set, and keep a backup of the operational database. That will be all for this session. If you have any question, please let me know. Thank you.